In this lecture, we will conclude our discussion on quicksort. We will also take a look at some special case sorting algorithms that take linear time. Let's go ahead and take a look at the code for quicksort. Once again, this implementation is already taken care of, so we don't need to write it as we go. You can actually follow along online, and I do recommend that you do so. That way you can actually see what's going on at each part here. So we got a couple things at the very beginning. Once again, this is all done in one file. We don't have a class that has the quicksort implementation and then a client that runs it. We just put everything into one file to make it simple. So we do have a cutoff variable, and this is to say that if our size of our array is small enough, we're going to use insert and sort, because as we discussed, it actually takes too long to do quicksort when the array is small enough. So we're going to say, well, once it's 10 or lower, we'll use insert and sort instead of quicksort. That's actually a lot faster. We have our main method where we have some array here we call quicksort. We'll then go through each element of the array and print the contents. So let's take a look at what's going on here. So the general form of quicksort is going to be that we're going to pass the array and then the range of the array to sort. So we're going to use this left and right. So our first quicksort call is the main call right here, where we're going to actually call quicksort again. So we're actually overloading the quicksort method, which is fine. So in our main method, we're going to call this version of quicksort, and that's going to call quicksort with specifying the entire range of the array as what we want to sort. So then let's take a look at what's going on inside of quicksort. So we first check to make sure that we're within the appropriate cutoff, because otherwise we can just use insert and sort. We'll see that in a second. In fact, I'll just show it to you now. So if this part is true, where if left plus cutoff is less than or equal to right, so we're saying that if the range that we're trying to sort is greater than 10, then we'll go ahead and use the quicksort approach. Otherwise, so if that's not true, we're going to call insert and sort, and we have the implementation of insert and sort down here, which is no different than what we've talked about before. This is the exact same code that we've discussed. We may just do some stuff with left and right variables, but that's really the only difference in this case. But it's the exact same implementation for insert and sort. All right. Now, inside the quicksort routine, the first thing we have to deal with is selecting the pivot. So that's being done in this line right here. Now, the easy way to do that is to use the median of 3 approach, where we're going to sort the left, right, and middle elements of the array. So let's take a look at the median 3 sorting approach. So here we go. So we first need to find the middle value, the center. So we're just going to take the indices of left and right and add them up and divide it by 2. And then we can just do 3 simple if statements for handling the sorting. So we'll check the element at the center and the left. Whichever one is smaller will be placed at the left. We then check the right and left elements. So whichever is smaller, we would swap to make sure that the left element is the absolute smallest. And then we just check the right and center elements, and whichever one is smaller of the two would get placed in the center, and then the largest one gets placed to the right. We see that we have a swap routine. I'll show that real quick, which is done right here. It's no different than any other swap routine we've talked about before. In some cases, this code is actually used throughout the program instead of just calling the method. In some situations, it's actually faster to do that. But in this case, we figured since we're just using the same code over and over again, let's just create a method, and that one method will take care of all the swapping. So we do all this swapping, and then the last thing we do with the median of 3 partitioning is that we do move the pivots over to the right minus 1 element. We put it at a right minus 1, and then we'll go back to our method up here. So here we go. So we get our pivots, and then we'll initialize our I and j values. So that's going to be our, I'll call pointers of where we're looking at, so we can actually handle the partitioning portion of the algorithm. So we initialize I to left, we initialize j to right minus 1. In theory, we would actually say left plus 1 and right minus 2 respectively, but we use the code here to have left and right minus 1, so that way we can avoid some special cases. This still works perfectly fine, no issues there. And what we just do is we'll increment I and decrease j until they're at the wrong spots, and then we swap the values. So that's what's going on here in this inner for loop. So, I mean, this is the real heart of the algorithm, was what's going inside this for loop. And you may notice we don't have anything inside here except the 2 semicolons. That's fine, because we're going to see that we have this break statement to get us out of the for loop whenever we need to. Okay. Now notice that we have 2 while loops inside this for loop, and they don't have anything in the body. And this is why quicksort is really fast, because this inner loop of the algorithm just has basically 2 increment and decrement operations by 1. So we just keep incrementing I until AI is less than the pivot, and we keep decrementing J until AJ is greater than the, or well, I guess let me say that again. We keep incrementing AI until AI is no longer less than the pivot if it's greater than or equal to the pivot. And we keep decreasing J until AJ is less than or equal to the pivot. That's when we know we need to do a swap. So whenever that happens, we're going to do a comparison. We do one test where if I is still ahead of J, we will then do a swap routine. Otherwise, we're going to do a jump. So the inner loop of our algorithm is just incrementing and decrementing by 1 test, and then we do a jump. That's it. That's why this is a really, really fast algorithm. There is no extra juggling compared to what we see in merge sort, where we have to merge sorted arrays into another array and do all sorts of copying. We're doing everything directly with A without dealing with any extra arrays or doing any extra copying. So once we've done that, we basically restore our pivot, and then we recursively call quicksort again for the left side of the array. So that's what's going on here. And then the right section of the array. And notice that in both cases, we don't have to include I, because I has the position of our pivot. We don't need to include it in our sorting anymore. So that's why we do a quicksort for left up to I minus 1. And then our second quicksort is from I plus 1 to the right. Now, one other thing I'll mention about these while loops is you may think it's tempting to rewrite these loops to include a body where we may set something like while AI is less than pivot, and then in the body say I plus plus or something like that. But what happens is if AI, AJ, and the pivot are all the same, we're actually going to get an infinite loop. So that is a problem. That's why we use this approach instead, which looks a little different from what you've seen before, but this does in fact work. In fact, to show it, we'll go ahead and compile and run this. So we'll click on compile. So it does compile. And let's see what happens when we try to do quicksort for this array here. So we'll click on run. And sure enough, we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that does look like all the elements here. Yeah. So this does correctly sort our array.